Problem 422. A very long cylinder of linear dielectric is placed in an otherwise uniform electric field E0. Find the electric field within the cylinder. So in order to do this, we're going to have to use Laplace's equation in cylindrical coordinates, which I solved in an earlier video. And we're going to also have to use our boundary conditions. So for this problem, I said, well, let's let E0 equal to E0 x hat, which is going to be my initial electric field. So we're also assuming that there's no charge, so rho is equal to 0, but there's still going to be some surface charges that still form. So with every negative that forms on this linear dielectric, a positive also forms, and this is going to be in the xy plane. And this symmetry causes our yz plane to have a constant zero potential. And in order to find this initial potential V0, we do our negative line integral of E dot dl, and we find that our potential is minus E0 x plus c, but at the origin, our potential is 0, so our constant of integration is 0. So V0 is just minus E0 x. But then we say x is equal to s cosine phi, so V0 is equal to minus E0 s cosine phi and we want that as s grows larger and larger away from a, the radius. So our boundary conditions say that the potential inside is equal to the potential outside at s is equal to a, and our partials are also going to be equal at s is equal to a. And then as our potential grows larger outside, as s grows larger and larger away from a, it's going to go to minus E0 s cosine phi. And of course, at the origin, there is no potential. So our Laplace equation for cylindrical coordinates, and again, we're assuming that there's no charge. So V of s of phi is equal to A0 plus B0 natural log of s plus the infinite sum from k is equal to 1 to infinity s raised to the power of k times a sub k cosine k phi plus b sub k sine of k phi plus the infinite sum from k is equal to 1 to infinity s raised to the negative power of negative k times c sub k cosine k phi plus d sub k sine k phi. So because of our boundary conditions, a naught is going to be equal to 0 because our yz plane has a 0 potential. Our b naught term is also 0 because as s approaches 0 in this case, the natural log of s is going to negative infinity. And we want c sub k and d sub k to be 0 because our potential inside a cylinder should be increasing, not decreasing. Inside increases, outside decreases. So our potential inside is going to be equal to the infinite sum from k is equal to 1 to infinity s raised to the power of k a sub k cosine k phi plus b sub k sine k phi. And that will be referenced later. V out, our potential out, is going to be with the same thing, but now our potential must be decreasing. Again, a naught is equal to 0 because our yz plane has a 0 potential. Our b naught term is equal to 0 because as s approaches infinity, the natural log of s also approaches infinity. And we must also satisfy our initial condition, which was our electric field and our potential from that. So a1 has to be equal to minus e naught. And when we set k equal to 1, we get s to the power of 1 is equal to a sub 1 cosine k phi plus b1 sine k phi. And ak is equal to 0 for all other values, and bk is also equal to 0 for all other values. But because we want the potential now to be decreasing, we still want c sub k and d sub k. So our potential outside is minus e naught s cosine phi plus the infinite sum from k is equal to 1 to infinity s raised to the power negative k times c sub k cosine k phi plus d sub k sine k phi. And the next step, we are now going to say our potential inside is equal to the potential outside at the barrier, the boundary. So we set them equal. So this is the inside potential and this is the outside potential. And what I did next was I added this to the left-hand side. So I made it all one side, and then from there on this side, what I did is I factored them all together. So I'm like, okay, well, this has a cosine k phi, and this one has a cosine k phi. So I said, okay, well, a sub k, a to the power k, minus c sub k, a to the negative k, cosine k phi. That's a series. And then I did it for sine as well. And then for the constant term, I have a constant term here, which is cosine. So I want constants from c sub k and a sub k pulled out, so I get these systems of equations. And in general, sine of k phi and cosine k phi are not going to be adding up to 0 all that much, except for some certain values. But in general, they do not add up to 0. Sine of x and cosine of kx will not add up to 0 because they're orthogonal to each other. So the infinite sums also have to be equal and opposite to each other in order for them all to add up to 0. But that just gives us the relation a sub k, a to the k is equal to c sub k, a to the negative k, and b sub k, a to the k is equal to d sub k, a to the negative k. Our interesting one is a1 plus e naught times a is equal to c1, a to the negative 1. That's the interesting one that we're going to use and to solve later on. Next we're going to do is our epsilon naught partial potential out over partial s is equal to epsilon partial potential in over partial s at s is equal to a. So in this step, I found out what I differentiated the epsilon partial s infinite sum, and there's only this s to the k, so s to the k differentiated is k s to the k minus 1 times these trig functions. And similarly, I did that with the outside potential, but now the s term vanishes here, and this s to the minus k becomes minus k s to the minus k minus 1 times these trig functions. And then from there, I set them equal to each other because that's what our boundary condition says. So I set them equal to each other, and then I move them all to the one hand sided on the equation. So epsilon, and then I also divided everything by epsilon naught so I could get epsilon sub r. So epsilon r times the infinite sum from k is equal to 1 to infinity, k s to the k minus 1, a sub k cosine k phi plus b sub k sine k phi plus e naught cosine phi plus infinite sum from k is equal to 1 to infinity, k s to the minus k minus 1, c sub k cosine k phi plus d sub k sine k phi, and that's all equal to 0. And I followed a similar fashion as before, where I'm like, okay, well, I have to factor it out, and I have two infinite sums. So I have sine k phi and a cosine k phi, and I'm like, okay, well, these leading coefficients have to be equal to 0, and this has to be equal to 0 as well. This is the only interesting one. The other ones are not so interesting. So epsilon r a1 plus e naught plus a to the negative 2 c1 is equal to 0. This gives me two equations that I have to solve. I'm solving for a1. So, and in order to do this, what I did is, in this equation, epsilon r a1 is equal to minus e naught minus a to the negative 2 c1. I multiplied this entire thing by a. When I do that, I get epsilon r a1 is equal to minus e naught a minus a to the negative 1 c1. And then from there, I added them together, and I add them together in order to cancel out these a to the negative 1 c1 term. So I get AA1 plus epsilon r, AA1 is equal to minus 2 E naught A. And I can just cancel out the A, so everything has an A, so just divide by A, divide it out. And I find that A1 is equal to minus 2 E naught over 1 plus epsilon r. And going back to our inside potential was the infinite sum from k is equal to 1 to infinity, s raised to the power k times a sub k cosine k phi plus b sub k sine k phi. However, we said that only k is equal to 1 satisfies the equation, but now we're saying a sub 1 is the only thing that satisfies, is the only non-zero term, I should say, actually. So our potential inside now is s raised to the power of 1 a sub 1 cosine phi. Well, we already found what a sub 1 was. So now our inside potential is minus 2 E naught over 1 plus epsilon r s cosine phi. And then we said, well, s cosine phi is x, so our potential now is our inside potential is minus 2 E naught over 1 plus epsilon r x. And to find the electric field, we differentiate with respect to x, and it's the negative derivative. So our electric field is now, negative derivative is 2 E naught over 1 plus epsilon r in the x hat direction. So 2 E naught over 1 plus epsilon r x hat, and then we use the relation epsilon r is equal to 1 plus chi e, and we substitute that into here. So 2 E naught over 2 plus chi e x hat is equal to E naught 1 plus chi e over 2 x hat. And it's a uniform electric field, just like in the spherical case. And that's everything. Thanks for watching.